Good. So, let's see. Thank you. Now let's share the screen. Good. My screen is being shared right now. Let's take a look at our schedule here, how we're doing, right? So Monday, we'll continue on 2D motion. We start the 2D motion here, and that's going to be the second time that we talk about 2D motion. And Wednesday is going to be our exam, our first exam, the day after tomorrow. And okay, so we will continue with 2D. We will continue with 2D motion today. First exam, the day after tomorrow, the day after tomorrow. Okay, from the exam is gonna be exam will be on Canvas from 8:50 a.m. to 10:50 a.m. Okay. So you must be logged into Canvas and this link with your camera on. Okay. If you don't have a webcam in your computer, if you don't have a webcam in your computer, you can use the webcam of your cell phone pointed towards you, right? Pointed towards you. Pointed towards you. What else? What else? What else? What else? Once you're finished with exam, once you are finished with the exam, you may leave. Okay, that's what's gonna happen. And now let's talk about 2D motion, right? 2D motion, and let's go back to our equations that we derived before for a projectile. Equations of a projectile. It's a set of 6 equations, equations of motion, right? Equations of motion of a projectile, a total of 6 equations. And let's go back what we did before. Let's see. Do I have it here? Doesn't look like I have it here. Nope. We have it here, and yeah, they are all here. Let's copy everything here. All right. Yeah, those are. We have the parametric equations, parametric in T, and we have the vectorial equations as well. Equations of motion right here. Okay, so we start with the acceleration. So we do not start with the position, right? Because we know we don't start with the position because we do know what the acceleration is at the beginning. Okay, that's our starting point. Our starting point is right in here. That's why we started with the acceleration. We start with whatever we know. Okay, and this, let's see here. I want this one, Vx. I don't need that. I'm gonna make everything simpler, right? X not equal to 0, and I put also a y not equal to 0 here. But, to make it very, more generic, let's put the x naught here. And we put the y naught here as well. Plus, right? More students coming. Here you go. Those are the parametric equations. It is possible to create a motion diagram using Excel. I didn't do that yet here in the classroom, right? But I'm going to show you how to create a motion diagram using Excel. Just by using those equations that you see right in here, we can create a motion diagram just by using those two equations here. Okay, we can create a motion diagram for a projectile, for the projectile motion. We can do that. Okay, and let's take a look at our Excel right in here. And now I'm going to do the following. I'm going to start with T, right? I'm going to first create a table in Excel, T in seconds, right? And X. Okay. First, before we get into the motion diagram of a projectile motion, okay? Projectile. First, let us do the motion diagram of a 1D object for motion diagram for 1D motion. Okay, motion diagram for, here you go, uniform 1D motion, right? Here you go, uniform 1D motion. Uniformly accelerated 1D motion. So you can have a feeling how this works, right? We're going to do also free fall motion. Free fall. I'm going to emphasize that is 1D motion. And then projectile motion, 2D. If you do those things, if you do this exercise there at home, you use your own Excel spreadsheet, you're going to start having a better feeling for these type of motions, okay? And it's not difficult to do that. Okay, let's start with uniform motion first. Yeah, I'm gonna write that down. Let's see how we're gonna do that. Yeah, let's write that down here. Uniform motion. Okay. And And how do I do? And I have to put the y here as well, okay? But because it's 1D motion, the y is going to have the same value no matter what. Remember, it's 1D motion, so I'm going to put 1 meter high. Let's say the object is 1 meter high. And then we're going to start t equal to 0, 1, 2, 3, 4, and so on, right? And what else I'm going to do? Let's say we start at the origin. And because it's uniform motion, okay, I'm going to put the velocity here as well. Meters per second. I'm going to put the velocity here in a single cell. I'm going to start with 1 meter. Let's start with 2 meters per second. 2 meters per second is equivalent to someone jogging in the beach, okay? That's what 2 meters per second is. Approximately someone walking in the beach. 1 meter per second is someone walking, right? 2 meters per second is someone jogging in the beach. And now I'm going to write my equation of motion. My equation of motion is going to be velocity times t, right? I'm making x not equal to 0. I'm making, let's emphasize that. X not equal to 0. And Excel is like I said before, Excel is a very useful tool. Okay. X naught v, and then I'm going to go ahead, write down the equation of motion right in here. Look here, x naught, but then I have to put a $sign here. So the row number doesn't change, stays at 2 because I have only one value here. Plus v, I do the same with the v. I put a $sign here times t. Okay. And now, because the velocity is 2 meters per second, for every second that goes by, you should have position 2, 4, 6, 8, and so on, right? I would know, I know what's going to be the, you go, the result. Oh, the result, going back here. The first 19 seconds. And now what do we do? The little trick here. The little trick is to plot x and y, okay? That's the little trick here. And now you have the path of the particle in the x and y plane. When I plot, see that? That's uniform motion. See, the distance between each of those points are the same. Okay? I can increase the velocity if I increase the velocity here to 4, right? What you're gonna have? You're gonna have a larger spacing between the points. Okay? Remember, I'm plotting y versus x, right? I'm not plotting x versus t, and that's the motion diagram for uniform motion. We can do that for uniformly accelerated motion, and I am going to copy that uniformly accelerated motion. Motion. Okay, there's a limit how many characters I can have here. Okay, and now I'm going to have what? I'm going to have V naught. I'll put it here and change the X by V. Change the unit to meters per second, right? What else I'm gonna have? I'm gonna have the acceleration. A meters per second square superscript. Okay. And now we can use an acceleration, whatever acceleration value is still 1D, right? 1D, her name, 1D, let's put 1D, uniform motion, 1D. Let's see if he let me do that. Yeah, he let me do that. I can correct that. Accelerated motion. Because it's going to be a 1D motion, the value of y is going to be the same. Make sense? I'm going to put, let's say, an acceleration of 1 meter per second square. Okay, it's going to start from rest. It's going to start at the origin. Going to start at the origin. And I have to come up here with the equation. Okay, x naught, already have x naught, right? X naught is F2. V naught T, already have the second term, right? And now I have to put the third term, half of A, put the dollar sign here, T squared. Write that right now, okay? At T equal to 0, the initial position is 0. And now we have, here you go, the particle accelerating. I'm not gonna do more than that because otherwise it's gonna be too much, right? Do you see that the motion is increasing in the delta x is increasing as time go by, right? The delta x increases. And we have, okay, we have done uniform 1D motion, uniformly accelerated 1D motion, and now we're going to do free fall 1D motion. Okay. And I am going, because it's going to be a free fall, x is going to be constant and y is going to change, right? Let me copy this one. Free fall motion is one special type of uniformly accelerated motion. 1D free fall. Motion like that. And now I just have to change my values here from x to y. So it's going to be a vertical motion, right? And I have to change, let's see, I have to change the acceleration. Acceleration is going to be 9.8 meters per second. Okay, it's not going to be x naught anymore. It's going to be y naught. So let's see, I'm releasing from rest from the top of a building. And instead of making it equal to 0, I'll make it equal to, let's say, 20 meters, right? Make it equal to 20 meters. Okay, that's the initial position here. I can click and drag. Okay. Let's see. I am, by the way, let's see. Oh, I made a mistake here, right? The mistake is that I have to put a negative sign. Okay. I have to put a negative sign. So you're releasing from the top of a building. So the velocity, the acceleration is going to be downwards. And I'm going to do more. I'm going to do every 0.2 seconds, okay? So I can have enough data points here. I have to do more here too. I have, let's say, I'm going to put 1 meter for x position. Remember, it is 1D in the vertical direction, right? Okay. So here you go. We are click and drag. Okay, let's see. We're getting to the bottom, right? 0.4 is about to strike. What's going on here? I think I know what's the problem. Let's erase it. Yeah, let's make it a little bit larger in the vertical direction. And now you have the motion diagram of a free-falling object just about to contact the floor. It's 40 centimeters, 0.4 meters above the ground. That's the last point. Again, see that the spacing, the delta y changes as time go by, right? And now we are going to do, projectile motion. Projectile motion is a combination of a vertical accelerated motion and horizontal uniform motion. It's a combination of those two, okay? And I'm gonna copy this one, duplicate the spreadsheet, and move uniform motion. What's going on here? Wait a minute, I did something wrong. Preform is this one. Oh, this one here. Okay, and this is going to be 2D projectile motion. Projectile motion. 2D projectile motion. So it and now we have to be specific here. We must have V naught along the y direction. We must also have V naught along the x direction. Let's see. Here's gonna be A sub x, A sub y, right? We have A sub x as well. At this point in time, you should remember that A sub x is going to be 0. Acceleration along the x direction. We are supposed to have V naught x. I'm going to change those numbers very soon. And we are supposed to have x naught. Okay. X naught is going to be 0. Y naught is going to be 0. We're propelling an object from the origin. And we are impinging initial velocity along the x and y direction. So let's say it's 45 degrees. If it's 45 degrees, let me give you 10 meters. It's gonna be the V naught y is gonna be the same as the V naught x, 10 meters per second. Okay, the V naught is going to be 10 square plus 10 square, 200, square root of 200. Okay. And we have the good. Let's see. Yeah, that's y. Y is okay. There's no problem here. I put positive, positive. It means that this one is upwards. This one, the velocity vector, is the right towards the right. X naught. X is going to be x naught plus V naught x times t. Oops. Okay, V naught x here times t. Click and drag, right? Oops, something wrong here. Let's see what I did wrong here. X naught plus V naught x times t. I don't see what. Oh yeah, that's because I didn't put the the dollar sign here. Okay, dollar sign here and dollar sign here. That's why I got 0 for everything else. Okay. Oh yeah, here you go. You see that? It does that automatically for us. Beautiful, right? So here you go. The motion diagram of a projectile. Okay. I'm going to get rid of this guy. Okay, we're going to see everything. Nice, right? We don't plot x versus t, don't plot y versus t. We plot x, y versus x to get the motion diagram. Okay. And we can change it for different speeds, right? Let's say I want to put 20 meters per second along the x direction and 10 meters per second along the y direction. You can calculate what angle that would be, right? Okay, notice that this graph is not in scale, right? If you want to have a more realistic display of this graph, you have to get the same spacing, right? This graph, to make it more realistic, we have to stretch in this direction. This distance that you see here in this graph should be the same as this distance, right? At this point in time, it's not realistic because we have 0 to 5 meters is this much long, whereas in the vertical direction, whereas 0 to 5 meters is this much long. So we have to stretch it even more to make it look more realistic, right? So this angle is relatively shallow. It seems to me that's going to be, we can calculate that, right? And the arctangent of 10 divided by 20, but I don't, it's going to give us result in radians. We want in degrees. Degrees. Like that. And what we get? 26 degrees. 26 degrees for this launch. So we have a velocity vector right in here, making 20 degrees, 26 degrees with the horizontal. And then as the particle climbs against the force of gravity, its velocity, its speed decreases. Not only is the speed decrease, but the angle of the velocity vector is going to become shallower and shallower. Okay? And decrease shallower until the velocity makes an angle of 0 degrees with the horizontal, because we have only a Vx value, right? Right here at the top. The y component of the velocity at this point is going to be 0. It's going to be 0, the y component of the velocity. And then after climbing against the force of gravity, now it's going to go down, right? Everything that goes up must come down. And now when it comes down, the speed increases. And the angle that the velocity vector makes with the horizontal is going to become steeper and steeper, right? Until it's about to strike the floor, the ground here. That's how we come up with those motion diagrams. I think it's a nice illustration of what you can do with Excel. Okay, so let's save it here. And there's more that we can do. There's more things that we can do with this equation, okay? With this set of equations. There is more. So we did all of that. 1, 2, 3, 4. If we have time later on, we do the uniform circular motion, okay? Uniform circular motion. But let's elaborate a little bit more on the equations of motion of a projectile. Let's elaborate a little bit more. Okay, there are lots of things that you can do with this set of equations. You know, the first thing that the first example. Let's say we can work out an example like this one right here. There are several examples that we can work. Here you go. Example: given V naught, G, and theta. Theta is the angle of launch that the vector velocity makes. The initial vector velocity makes, and theta. Here you go. I'm gonna put that where theta is the initial angle that the velocity vector makes with the horizontal. Write y as a function of x using the equations of motion. Oh, there's more. It's not just v naught, right? Even v naught, x naught, y naught, v naught, g, and theta. Write y as a function of x. Okay? So we have notes that we have two parametric equations for the position of the object in the two parametric equations. Two parametric equations in T, right? In T, for the position of the object. What do I mean by two parametric equations? I mean x as a function of t and y as a function of t. Okay? And then what we want? Now we want to replace t with x in the y versus y of t. That's what we want to do. So here you go. Those are the equations. I'm going to emphasize that this x here is a function of t. I'm going to emphasize this y here is a function of t. Okay, t and t. And I can take out this x naught, right? From here. And I'm gonna take out this x naught here too. Because I want to keep this equation written in the most generic form. So what can we do? Okay, in order to do the above, we must eliminate t from this system of equations. Okay. Okay. That's what we want to do. In order to eliminate t from this system of equations, in order to do that, we must write t in terms of x or t in terms of y as a function of x or y. Which one is going to be? And then the next question is, which one are you going to choose? Are you going to write t as a function of x, or are you going to write t as a function of y, right? Which one? The question is, which one is the most convenient? Which one is the most convenient, right? To do that. to the above. Okay, look at those two equations here. This one is far more complicated from this one, right? Compared to this one. If I write this one in terms of x, this one here is going to be a linear equation. But if I write this one in terms of y, what's going to happen? This one here is going to be a quadratic equation. There'll be a square root there. There'll be a complicated, there'll be two solutions for t. Okay? So definitely, this one is going to be more complicated than this one. Because of that, we're going to choose to write t in terms of x. Okay? To write t in terms of x is far. And why am I doing that? Once I write t in terms of x, I will substitute it right here in the equation for y. Okay? And our final equation will have a dependence of y in terms of x. Okay? It's far more convenient because it will result in a simpler equation compared to t in terms of y. Okay? 9:28. Let's see if there is anybody else there waiting for me. Let's see. Yeah, nobody waiting in the waiting room to get checked in. Okay, so here we go. I will copy and paste those two equations here. So for t, first step in solving for t is this one here, right? I'll keep my second equation there. I'm not gonna do anything else. Next step to solve for t, yeah, is to divide, v naught cosine of theta. And now x is no longer a function of t, right? Well, it's still a function of t, yes. It is still a function of t, but we don't need to carry it. Okay? So here you go. That's what I want. And then what's the next step? The next step is to plug this t right in here. Okay? That's the next step. And I'm going to copy that, paste it. I'm going to replace the t here. I'm going to replace the t here. Okay? One t is going to be linear. The other t is going to be quadratic. Okay? And now the y is no longer a function of t. Why is that? Because that t that I put in there is a function of x. Now my y is a function of x. Okay, like that. Let's see what else we can do here. I'm gonna, now this is no longer a parametric equation. Okay. And I will erase that. What else can we do? Okay, this V naught here can cancel out this V naught, right? I'm going to emphasize that. This sine of theta, I'm going to put that in red, is going to combine with this cosine of theta. Okay? Now we don't need this guy anymore. Okay, I will stop writing it. I already use it, so I don't need to combine. Here we go, V naught cancels out with V naught. And the sine of theta divided by cosine of theta becomes tangent of theta. And I don't need to keep it in red anymore. Yeah, don't need to keep it in red anymore. Let's see, what about here? Okay, I'm going to distribute that square. Distribute. Didn't work. Why is that? Let's see. Okay, worked. Now it worked. And raise to the square. Now I don't need any of that anymore. That's the variation of y with x. Okay. If if and if the initial position vector is at the origin of the coordinate system, meaning x not equal to 0 and y not is equal to 0, then the above equation reduces to okay, x, right, and x squared. Not supposed to be bold-faced. Okay, that's the equation that we get. Oh, why not is 0, right? So let's get rid of this one as well. And that's the path of the projectile. The path of the projectile, I'm going to elaborate a little bit more, okay? And don't forget, this is the initial angle of launch. The initial launch angle of the projectile. So let's see, I'm going to take this x squared from here to put it in a more familiar fashion for you. And I'm going to put the g upstairs. Notice that we have a negative sign here. All of that here is constant. That guy is a constant too. Okay. So comparing that to the equations, it looks just, let's say, it will to the equation that we already know, right? And I'm gonna put like this thing, this term here is gonna be my bx squared, where b is less than 0. Okay. B is less than 0. Even better. I'm gonna emphasize that b is positive. I'm gonna emphasize that we have a negative sign here. That's why I'm making b. B is this guy here. G is always positive, 2 is positive, cosine squared is positive, b naught squared is positive, right? So I'm gonna write down like that. B equal to, I'm just rewriting those terms. And this guy here, I'm gonna call it C. Okay? If you look at this equation, you can clearly see that this equation represents a parabola with a concavity pointing downwards, right? Exactly that, this drawing that you see here. Let me go back to my pen here. Yeah, I'm gonna shrink this guy. Okay, this is Y, this is X. Okay, so C is a parabolic shape with a concavity down. That's exactly what this guy is telling us. Concavity down. Okay. So let's write that here. This one, like that. You don't have to memorize that, but you have to become familiar with it. Okay? That's one example out of the way. There are more examples that we can work with. And okay. Next. Given a projectile is propelled with a known velocity, initial velocity, magnitude, and direction, non-initial velocity, magnitude, and direction, theta, right? With a non-initial speed v naught, let's put it this way, initial speed v naught, and the direction, theta. Find the height of the highest point of the projectile along its trajectory. Okay? The initial position of the projectile is at the origin of the coordinate system. Okay? The height of the highest point of the projectile. Okay, we're going to go back to our equations of motion here. And remember what I told you, right? Here, the equations of motion, the equations of motion for the position are that. Yeah. What we want to know? We want to know why for an instant of time t, where this y has a maximum height. Okay, we need to find y for maximum height. In order to do that, we must, one way, in order to do that, one possible way is to find the instant t in which the projectile reaches its maximum height. Okay? And there is a condition for maximum height. And there is a condition for this maximum height. Okay? So you have to go back to our 1D equation. If you propel an object upwards in one dimension only, the object is going to reach its maximum height whenever its velocity component along the y direction is 0. Okay? Make sense? This maximum height is achieved whenever Vy is equal to 0. Make sense? Because of that, okay, my light turned off here. But I have my UPS device here that picking up on the electricity. Let's hope it lasts long enough. Okay, came back. Electricity came back. Good. Okay. Because of that, we must use the equations of motion for the velocity component, right? For the velocity components. Let's go back. Let's hunt down that velocity component. Yeah, right in here. Right in here. Okay. And there's more. Because we want to know just the maximum height, we're not going to need this x here. Okay. We want maximum height, then Vy must be equal to 0, right? Similarly, because similarly, we're not going to need this guy either. Okay, but let's keep it in there. The condition, okay, applying the condition for maximum height, Vy equal to 0. We have, here you go, Vy equals 0. Okay. So for t, okay, that's the technique that we use, right? We have that, right? Next, I pass the minus gt to the other side, and we get that. We solve for t. We get that, something like that. So we get the instant of time in which the maximum height is going to be, in which the y component of the velocity is going to be 0. Okay? At this instant of time, at this instant of time, the y component of the velocity is 0, and the projectile reaches its maximum height. Okay? Okay. And now that we have, and even going to emphasize maximum. Oh, no. Hey, Excel doesn't like max in there. So gotta trick it into doing what we want here, right? And the same thing, maximum height. Oh, again, made a mistake again. Here, maximum height is reached whenever t equal to t max, right? We go ahead, replace here t with t max, t max. Yeah, better. I like this notation better here. Max. Oh, let's not forget y naught is 0, right? So I can exclude this y naught here, yeah. And let's replace it. I'm going to take away the t functional dependence. And I will place this guy right in here. And I'll place this one right in here. And let's square it. Okay? Let's see, what else can we do? Can we simplify that? Yes, we can simplify that. There is still something that we can do. Let's see if that leaves V naught. I'm combined with V naught, right? I'm combining one V naught with the other one. And then I'm combining this sign with this sign here. And then I do the same here. Square the V naught. Square the sign. Oh, I squared the wrong one. There you go. Square the sign. And square the G. Now I don't need the square anymore. The square after the parentheses anymore, right? What am I doing? Yeah, okay, I gotta put this guy downstairs. Yeah, that's correct, right? That's the more correct way. I combine V naught with V naught. I combine sine with sine. I square V naught G and sine of theta. Okay, everything is squared here. And I'm going to simplify this G, right? I'm going to emphasize here, bold, bold. And I will continue my derivation. Okay, this G cancel with the other G. No longer a bold face. Okay, now notice what we have. This term here is exactly equal to this term here. So you can put it in evidence. Okay, and that's what I'm going to do now. I'm going to put this term here in evidence. Okay, because this guy here is in evidence, what goes inside the parentheses in this spot here is going to be the number 1. Okay, which will be subtracting from half. So we finally have the final result. Max height is going to be half P naught square over G sine square of theta. Okay. We can go for another example. It's 9:50 now. Let's take a little break now before we go to the next example. But in this meantime, I want you to try to solve it on your own for the next example. Find the angle of maximum range. Find theta, right? For maximum range. For maximum range means, or distance over a flat surface. Given initial velocity x naught, what's the angle of maximum range, right? Think about that. And we're going to take attendance now. Lecture. Today is the 30th. And how many students we have? We have 20 students. That's good. Audrey Aguilar. Are you here, Audrey? Oh, yeah, thank you. Next, Matthew Aguirre Mata.
Here.
Thank you, Matthew. Darius Blunding.
Morning.
Did you say anything? You're very
Morning.
low.
Can you hear me?
Okay, thank you. And Brianna Carrillo, are you there, Brianna? Okay, thank you, Brianna. Jazzy Castellano. Thank you, Jazzy. Gabriel Contreras.
Here.
Thank you, Gabriel. Oops. Liliana Cortez. I don't see Liliana here. Okay. Next is Juan Escalera. Are you there, Juan? Doesn't look like. Okay. Next is Molly.
I'm here.
Molly is here, right? Next is Henry Kim.
Here.
Thank you. Ruth Bandujano. Let's see if Ruth is here. Ruth. I don't see Ruth here. Noemi Martinez. I don't see Noemi either. Next is Danae Miller. Hello, Danae, are you there? I see Danae in my roster here, but I don't hear from Danae. Let's go for the next. Ramon Olivares.
Here, Professor.
Thank you. Taylor Forn.
I'm here.
Okay. Next is Alexis Quijada. Alexis hasn't been coming for some time. Stephanie Ramos.
I'm here, Professor.
Thank you. Jeremiah Reyes. Thank you. Next is Sean Rosario.
Here.
Thank you. Next is Ali Standard. Hey.
I'm here, Professor.
Okay, Ali here. Thank you. Jason Straight.
I'm here.
Okay. Elena Trujillo. I see Elena here in my roster, but I don't hear from her. Next, Jason Valadares.
Here.
Thank you. Next, Stephen Vathapali. I don't see Stephen either. L'Oreal Williams.
Here.
Thank you. Nuhamin Wandimu. Oh, Elena, right? Elena. What about Nuhamin? No, I don't see Nuhamin. Next, Alia Zavala. Okay, let's see, 19. I have 19 here. 19. Danae, are you there? 19 here plus this 120, so the numbers match. Okay, thank you, Danae. Now we have 20. 9:55 right now. Break. 9:55 a.m. to 10 a.m. Any questions? Before going to break? Okay, if you don't have any questions, I see you in 15 minutes. Bye-bye. See you soon. Let's see. Sharing course. I'm back here. Here's our, let's take this one out of the way. Okay, and that's, you see my notes, right? Okay, so the idea here, given the same velocity, the same initial velocity, find which angle produces the longest distance, the maximum range, okay? That's what we have to find out. And by the way, maximum range is achieved, let's see. Yeah, solution, right? Let's go here. I want this one right after the break. Here you go. Better. Going back to our equations of motion for the position, right? That's what we want. Okay, maximum range means, here you go, maximum range means, oh, my goodness, my typing skills here are terrible. But it's not my typing skills, it's my, the one that I bought recently. Okay, maximum range means maximum horizontal distance. Okay, that's what it means. And the maximum horizontal distance obviously is going to be given by the x component of the position, right? And again, we are assuming that x naught is 0, y naught is going to be 0 too, right? That's what we have. So what we have to do? We have to find out the instant of time t, okay, for which x is going to be the longest, okay? Another way okay, is a, let's see. This is a two-step problem, okay? This is a two-step problem. One. First, you find out what is the instant of time t in which the object reached, in which the object, the projectile, impacted the ground. That's what you have to do first. And go right here. So going back to my motion diagram, you have to be consulting those things, okay? You have to have in your mind that the path of the projectile is going to be a parabola, okay? So here you go. You have to find the instant of time in which the projectile, impacts the ground right here. It starts at the ground floor, y not equal to 0, and then impacts the ground floor again after some time, y final equal to 0, okay? And in order to find out this instant of time, you have to use this equation here, okay? You find that by using the y of t equation. After that, After that, you substitute t for x, right? In the equation for x, in the equation for x, and analyze the resulting equation for the best angle, right? For the best for the angle that maximize this x. That's how you do it. The two-step approach. Okay. So let's go ahead and implement this two steps. Okay. So, we gotta make y equal to 0. Okay. And then if we make y equal to 0, we will find the time of flight of the projectile. Going back again, I'm going to emphasize here. Here is a t equal to 0, y is equal to 0, right? And a t equal to some value that I still do not know at this point here, just before impacting the ground, the y is going to be 0 as well, okay? So what you have here, you have an equation, a quadratic equation that, in t, here you go, quadratic in t. This term is the linear term, this term here is the quadratic term. Because it's quadratic in t, you are going to have two solutions. One is for t equal to 0, right? If I make t equal to 0 right here, this equation is satisfied. And the other, we are going to find now. Here you go. And we're going to find that now by putting t in evidence. Here you go. This t here is the quadratic one, and this term here is the linear term in t. See, for t equal to 0, this equality is satisfied. But then for this term here is equal to 0, we also have this equation satisfied, okay? And the one that we want is this one right here. So here you go. Two solutions, right? But the solution that we want is not t equal to 0. We want the other solution, this solution here. And that the solution gives us the time of flight while the projectile is still airborne. How long the projectile stays airborne. One more here. And I put my 2 right here and divided by g, right? I put t equal to v naught over g sine of theta. And now we substitute this one here into this t. And then we have the range of the projectile. Right here. And we can go another step. Let's see if we can simplify. Yeah, we can simplify. We're going to combine V naught with V naught, right? This V naught already combined there. Let's see what else can we do. I'm going to get this V naught square. I'm going to place it right in here. And then what else I'm going to do? I'm going to place this term here in front. Okay. And then there is one more thing that we can do. I'm going to put this 2 right here in front of the sine of theta, cosine of theta. If you go back to your trigonometric relations, you find that this term that you see right in here can be written down in a better format, in a different format. And this, okay, recall that from your trigonometry class, that this term here is going to be given by 2 sine of 2 theta. Okay? Remember that? And here you go. Now I can write that down, that my range R, right? I'm going to put range R here is equal to, oh, it's not 2, sorry, it's just sine of 2 theta. Okay? Sine of 2 theta. So this guy here becomes sine of 2 theta. I'm going to even write that down here, x max. Oh, gosh, again. Here you go. Got it. X max is R for range. That we did the first part, the first step. That's our first step. I don't need this term anymore. Let me get rid of it. Okay? But I'm going to need this equation here. And now we have to figure out which angle I have to use to maximize my R. Okay? First, let me summarize here. First, we determine the range of the projectile for any angle. Okay? Now we have to find out what angle maximize the range. 2 steps. And let's look at this guy here, right? Okay, so we must find theta. So this basically, this problem reduced to find theta. So the sine of 2 theta is equal to 1. That's what we have to do. Okay, the maximum value of sine of 2 theta is going to be 1. Okay? To solve this problem, we must maximize sine of 2 theta. Its maximum value will have to be 1. Well, I'm going to even put plus 1. Okay. So here you go. Whenever sine of 2 theta is 1, we maximize the range. And now we have to find out which angle theta, provides this value for 1, right? Well, sine is going to be 1 whenever its argument is equal to what? Whenever its argument is equal to pi. Oh. Here? Yeah, pi. Okay, pi over 2, sorry. Whenever the argument of sine is pi over 2, the sine is going to be 1, right? So what you must have here? You must have that 2 theta must be equal to sine of pi over 2. Make sense? Okay. Consequently, two theta must be equal to pi over 2, like that. And then what do we get? we get that theta must be equal to pi over 4. Okay? So we maximize the range whenever the projectile is launched at an angle of at an initial angle of 45 degrees. Okay? We can discover all those stuff from those equations. Cover all those things from those equations. There is another way of solving this problem. There's another way of solving this problem. Okay, another way of solving this problem. Is by using the first result we got. Remember that before? Let's take a look at. Here you go, y as a function of x. The very first result we got. Let's see. Here you go, this one here. Okay. So now instead of finding the instant of time, all we have to do is to find the x, right? For y equal to 0. If y is equal to 0, we will get the range for x, right? Actually, we get two solutions, just like we got for the t, right? Here you go, y equal to 0, right? X become the range, and now we have two solutions for x, just like we had before. One is for x equal to 0, the other one is for x equal to the range. Here you go. Here you go. What we want this solution here, right? And not the other one. So use the following solution. Use the following solution. Equal to 0. We are supposed to get the same result as before, right? You go there. Cosine, we solve for x. 2 tangent 2 V naught square. 2 V naught square cosine square theta, right? And then I have to divide by g. I still have to divide by g, right? Okay, so we got rid of the 2 here of the half on the right side. We got rid of V naught cosine, V naught square cosine square. We got rid of g. And that's my equation for my range. Is it exactly the same as the other one? Let's see if it's exactly the same as the other one. Huh? Not yet, right? Compare what we got before. We got something like that. The V naught over G we have here. We do not have the 2, we do not have the cosine square, we do not have the tangent theta. But we can continue working in this equation to see if it reduces to this equation, right? The first thing that that's kind of obvious to us is that the tangent can be converted into sines and cosines, right? And I'm going to emphasize that this term here is the tangent. Okay, this term here is the tangent, right? Do you see that the cosine cancels out with the cosine now? So we are in the right direction. Oops, it looks like we are going, oh, what did I do here? Yeah, okay. Go, cosine cancels out with this other cosine. Right? I'm gonna put the range here on the left side. And now it's starting to look like what we got before, right? It's not exactly what we got before, but if we go back in our derivation here, okay, that we substitute that, that's what we got, right? We can see that it's exactly the same term, right? 2 cosine sine, 2 cosine sine, b naught square over g, right? And then we finally conclude that the range, just another way, right, of is going to be that. Okay, let's see. I think if you have one more here. Yeah, okay, so that's all we have here for projectile motion. Let's see if I'm forgetting anything there in the book. Let's take a look here. Wiley plus. Let me see. Any questions? You know, take this chance to ask any questions if you have. And let's go to Wiley plus. Oh, it looks like I have it here. Okay, not this one. Or this one I want. Wiley course resources. Launch. We are doing kinematics in 1 dimension. Displacement, velocity, and acceleration, equation of kinematics in 2 dimension, projectile motion. Right? That's what we have here. This is another example of projectile motion. Okay. An airplane releases a package, and the package moves just like a projectile. If the plane is moving at 115 meters per second, when the package is released, the package is going to have the same velocity, the same initial velocity. And what he's asking from you, following care path package. The direction of the right have been chosen. The plane releases a cat pack that falls on the ground along a curved trajectory on air resistance. Determine the time required for the package to reach the ground, to hit the ground. Right?
Can we
So
do this example, Professor?
What?
Can we go over this example?
One minute, let me raise the volume. Can you repeat, please?
Can we go over this example?
Yeah, let's do it. Here you go. Shows an airplane, right? Moving horizontally with a constant velocity 115 meters per second at an altitude 1050 meters. The directions to the right and upward have been chosen as the positive direction. Okay, the plane releases, here you go. Plane releases a care package that falls to the ground along a curved trajectory, ignoring air resistance. Determine the time required for the package to hit the ground. Okay. So go back to your equations of motion for the projectile. Okay. The airplane, because the airplane is flying along the horizontal direction, it's not climbing, it's not going downwards. The initial velocity along the y direction is going to be 0 meters per second. Okay, so this case here is just like this half of the parabolic trajectory. Okay, here is your package. Forget what you have in your left side. Okay, and the package is going to have this horizontal velocity that's going to be exactly the same as the velocity of the airplane. Okay, that's the key piece of information that sometimes people don't understand. Okay. So because the airplane is moving at 115 meters per second, the moment you release the package will also have 115 meters per second. The difference is that the airplane is going to keep on flying the horizontal while the package is going to move both in the horizontal direction and the vertical direction. Okay? That's what you have to keep in mind. And then how long is it going to take for the package to reach the ground? Okay, you gotta go to the equations, right? To the equations of motion. Let's get the equations of motion. It is example number 3. I'm gonna do that in my notes. Okay, in my own way. Okay, example 3 in the book. Okay, solution. The equations of motion, let's get that. This one right here. I'm gonna need that, okay? Y of t is equal to, okay, I gotta put in this case, we are going to have a y naught different of 0 because the package is at a given height, at the initial height of the plane, right? Right here. The initial velocity of the package in this case is gonna be 115 meters per second. And the angle of launch is gonna be what? It's going to be 0 degrees, the initial angle, because the plane is flying the horizontal. Okay, so this angle theta here is going to be 0. Okay, so because the plane is flying along the horizontal direction, the initial angle, the angle of launch, the launch angle of the package will be 0 degrees. My goodness, what am I doing here? Here you go. 0 degrees, okay? Consequently, and the package, so consequently, this term here is going to be 0. I'm going to put 0 here. 0 degrees. And put a no, so it looks nicer. Okay. right? And then this term goes away. Okay? And that's what we have, the equation of motion along the vertical direction only. Oh, along the vertical direction only. We want to find t whenever y is equal to 0, okay? We want to find t whenever the package hits the ground, or y equal to 0. And let's write it down. We want to find t whenever the package hits the ground, or y equal to 0. So let's do it. All right, we go. Here is 0. I pass this term to the left side, or or pass the y naught to the right side, right? And now we can solve the equation 2y naught over g, right? The 2 already passed to the left side, the g I passed to the left side. And now we have to take the square root of that to solve our problem. Square root right in here. And I will put my t on the left side. Is that what the book told us? Is that the equation that the book told us to use? Let's see. Right in here, 2y, 2y naught over g, okay? 2y naught over g. The book basically did a different axis, okay? He's putting the origin of the axis right in here. The origin of the y-axis right in here. I'm putting the origin of my y-axis right here on the ground. So I did differently. And now all you gotta do is substitute the values there, right? What's y naught again? Y naught is 1,050 meters. 1,050 meters. G is approximately 10 meters per second square. It's okay to use 10 meters per second square in our problems, but the error is going to be very small. I can cancel the 0 is this 10, right? This 0 here gets canceled out with this 10. This meter cancels out with this other meter. This second square can be put upstairs. Okay. I don't need this one here anymore. And we are left with this multiplication here. 2 times 105 is going to be 210. 210 seconds square. And now you gotta take the square root of 210. The square root of second square is seconds, right? Seconds. What's the square root of 210? Let's take a look here. Oh, let's take a look even better. Square root with my Excel is QRT 210. 14.5. 14.49. Is that what he said? He got there in the book. Let's see. 14.49. Oh, he got 14.6. Okay. He got a little bit less because he's using 9.8 meters per second square. I got a little bit more than him because I used 10 meters per second square. The difference is very small. Okay, if you got what, let's see, 4.49, 14.49, let's see, yeah, 14.5 is 1 in 146, less than 1% difference. Okay, Did you get that? Want to hear from you? I did the solution slightly different from the book. Okay, the book used what was the difference? He put the origin of his y-axis right here at the top, where the airplane is flying. I put the origin of my axis right here at the bottom, but the result is the same. Okay, next one here. Let's see. Okay, so he's providing another solution here, part of the solution, right? Velocity of the cat. Then you can get the velocity. Show the. Okay, let's see. Example 4. 3.8 shows this package as package B. Okay, ignoring air resistance, find the magnitude of velocity and the direction angle of the final vector velocity. Okay, that's what it's asking now. To find the velocity, you have to use those two equations for the velocity, right? Example 4. Example 4. Find the speed just before impacting the ground and the angle of the velocity vector. Okay, velocity vector. That's what he's asking. Solution, what you have to do? Solution. Find Vx and Vy using the equations of motion. I'm going to give you, equations of motion, right? Then, after that, find the angle, right? Find the angle of impact by using, the Vx and Vy is going to be what? Vx we already know is 115 meters per second. So let's write that down here. Because the motion along the x-axis is constant, 115 meters per second. Oops. There's no secret here for Vx. It was released from the airplane at this speed, but what's going to give a little bit more of work is going to be to find the y component of the velocity, right? The y component of the velocity is going to be initial velocity along the y-axis minus ge. Okay? If you recall, the initial velocity along the y-axis was 0 because the package was released along the horizontal direction. T we calculated before, right? And we don't need that. G is 10 meters, approximately 10 meters per second square. T, what do you get for T? 14.5. 14.5 seconds. 14.5 seconds. Okay, and I want to put this 115 outside the ratio. And then you do the math. 145 meters per second, but this is the vector velocity is downwards. Vector 145 meters per second. This second square cancel out to the second. Okay. This one. And now you combine those two velocity vectors. You can get here. Here you go. Let's see. So one velocity vector is 115. the other velocity vector, the other component of the velocity. I meant one component of, oh, what happened here? One component of the velocity is 115, the horizontal one. Let's see, this one, right? The other one is 145. I'm gonna make it a little bit larger. The resulting final vector is this one right in here. I'm doing the parallelogram method. Right, and this is one here. Yep. So you want to find out this angle here. Tangent of this angle is this 145 divided by 115. Okay, let's take a look at the book. Okay, so he goes. Let's see what he did here. V naught y. Yeah, find the v, right? Final velocity. Oh, he's doing cosine. Okay, he's doing a different way. I'm doing the tangent. I feel it's easier. Okay, but he's asking for what? Let's see. Find the magnitude. Yeah, find the magnitude of v and the directional angle theta. Okay, the magnitude of v is going to be 115 square plus 145 square is square root of that, right? So let's write it down. Thank you. V square Vy square. No. Plus Vx square, right? That's what that, so yeah, and then you can get the, take the square root of that, you get the angle. And then to find the direction, it's the theta angle going back here to this drawing, right? This angle theta, tangent of theta. Tangent of theta. I prefer to do the tangent. He's doing that with the cosine. Is Vy Vx. Like that, right? And then you solve for theta. Let's keep on going. Let's see, what time is that? 10:55. And let's see, conceptual. Here you go. The guy kicking the ball behaves like a projectile, okay? Physics of hang time of football, okay? Hang time, how long will he stay airborne, right? Hang time means how long the football player stays airborne. Range of the kickoff. Okay, and then you have other types of problems. Propelling the projectile at this angle, propelling the projectile at this angle. Okay, the equations are the same, but you have to think a little bit how you do that, okay? Any questions? 10:56. Let's see, there's a student who arrived. Let's see. Let me go back to my don't see my list of students. Let's see what's going on here. Ah, here you go. I got it. Let's see. Ramin, are you there? Okay, Stephen Lavapali. I don't see Stephen. Alexis Quijada. Noemi Martinez. No. Juan Escalera. Ah, Liliana came in, right? Are you there, Liliana?
Yes, I'm here.
Yeah. I knew someone was here. And B21. And okay, let's any questions before we go in our break? Our second break, right? Break 10:57, right? AM to 10:15 minus 3 is 10:12 AM. So I see you in 15 minutes. Bye-bye. I'm back here. Let's share the screen. And now what we're going to do, we're going to do relative velocity. Okay, and okay, that's I'm going to give a very simple, and the book also has here a very simple example of relative velocity. And then we are going to get into a more generic way, into a more generic theory of relative velocity, okay? So let's, all right, here, relative velocity. A very important concept, okay? Very important concept. Very important concept. It's we will revisit this concept in physics 7 when we cover special relativity. Okay? When we cover Einstein's, right? Einstein's special relativity. So remember that. The simplest, and let me get, see if I have an illustration here for relative motion. We don't have it here. Let's see. Motion example. Let's see here. Nope. That's CL. CL. P37. I have to do from scratch. I have to do the drawing from scratch. Let's see. Yep. Yeah, let's do the drawing from scratch. So I don't spend too much time doing that. Relative velocity. Okay. Okay, every time we are driving in the freeway, the speed is the speed that is displayed. It's the speed that is displayed in the speedometer. Is automatically assumed to be the speed relative, okay, I'm going to emphasize it here, the relative to the freeway, right? There's no doubt about that, right? However, in physics, this is not necessarily so. This is not necessarily so. Necessarily so. You can have the speed. You may have the following relative speeds slash velocity, right? Can be speed or velocity. The speed slash velocity relative to the freeway. Accordingly, you may have the following relative speeds. One, the first one that we already talked about. And now I'm going to keep on talking about velocity, right? Velocity with respect to the ground, right? This slash freeway. That's the most obvious one. But you can also have, let's say the velocity with respect the car ahead of you. Okay? You can have it. The higher the velocity, the higher the speed, right, of your car with respect to another car in front of you, the higher the likelihood that you're going to have a big damage to your car. You're going to damage your car big time, the higher the speed, right? That's why it might be important that this relative velocity. But then let's say velocity with respect to a jogger, to someone jogging along the freeway, right? Can be the velocity, by the way, with respect to the wind that's blowing outside your car. This is very important if you're an airplane pilot. This is very important. You have to keep track of the direction of the wind. If you have a tailwind, you're going to fly faster with respect to the ground. If you have a headwind, your speed with respect to the ground is going to be lower. Okay? Velocity with respect to the wind that's blowing outside your car. Okay, and then you can think of many other, let's say the speed and others, okay? Okay. This thing is especially important if you're, for instance, what about a ship, right? What about a ship? What about a ship that is navigating in the high seas? Okay. Okay. For the case of the ship navigating in the high seas, you can have the following velocities. Velocity with respect to the seashore, right? The velocity with respect to the water current, which, by the way, is going to affect your velocity with respect to the seashore. If the water is calm, if there is no water current whatsoever, then the velocity with respect to the water will coincide with the velocity with respect to the seashore, okay? Let's put this one here, okay? If the water current, if the water is calm, right? It's calm. In other words, its relative speed with respect to the seashore is 0, okay? Then the velocity of the ship with respect to the seashore will coincide with the relative velocity with respect to the water current, right? Which other, velocity with respect to the wind that's blowing out there in the sea, right? Out there in the sea, right? And so on. And so on. And then we can go to a higher level here. Instead of finding out what's the relative velocity of a ship, right? What about the relative velocity of an airplane? What about the relative velocity of a rocket in outer space, right? Outer space. And in the case of the relative velocity of a rocket in outer space, then now you can start talking about the relative velocity of a rocket with respect to the Earth, to the center of the Earth, let's say, or the relative velocity of the rocket with respect to a point in the equator in the Earth. The relative velocity of the rocket with respect to the sun, the other star, another planet, okay? For the case, so let's write that down here. For the case of a rocket in outer space, we have several other possibilities. Okay, here you go. One, the relative velocity of the rocket with respect to the center of the Earth. But you also can have the relative velocity with respect of the rocket with respect to the point of launch, Cape Canaveral, for instance. Point of launch, like Cape Canaveral. Okay, and You can also say the relative velocity of the rocket with respect to the moon, which is going to be different. Okay? The relative velocity of the rocket with respect to the sun, with respect to Mars, and so on. Do you get the idea? Scientists, they need to know, especially rocket scientists, they need to know all types of relative velocity to get their spacecraft navigating in space. Okay? And they use those ideas of relative velocity. Pilots, pilots that are flying an airplane, they also need to know their velocity, their relative velocity, mostly with respect to the ground. But they also have to know their relative velocity with respect to the wind that's blowing, so they can orient their aircraft properly to get to their specific destination. When I was a pilot, right, I used to do that. I used to do those computations, okay? With the computers, with the analog computers we used to have there in the aircraft. And that's the importance of this concept of relative velocity, okay? But let us talk about the simplest relative velocity example, which I already mentioned out there, okay? So I'm going to make a drawing. And I'm going to draw my axis. This one, I'm going to take advantage of this axis here, what we call the referent axis of reference, okay? This axis of reference is attached to the ground. That's how we draw our axis of reference, okay? And let's say I have someone jogging along the x direction of the axis. Okay, let's see. Here you go, velocity to the right. And let's say the velocity of this guy, okay? Velocity. I'm gonna call this guy number 1. And then his velocity with respect to the ground. Let's say I told you that our speed, right, whenever you're jogging is around 2 meters per second. And that's the notation that I'm using here. And even better, this is gonna be individual A, okay? Individual A. So I'm going to get, and instead of 1, I'm gonna put individual A and capital G for ground. The velocity of the individual A with respect to the ground, let's say, is 2 meters per second to the right. And I need to do my subscript here. That's how we usually do our notation, okay? Velocity of A with respect to G. Okay? And now we have someone else. Instead of jogging, he or she is walking. He or she is walking to the right as well. And this gonna be individual B. Because it's walking, he or she is walking, their speed, velocity of B with respect to the ground is going to be just 1 meter per second. This is a very simple problem. The question I'm gonna ask you, let me shorten my arrow, right? Here we go. Go ahead, do the drawing, And the question I'm gonna ask you, what is the velocity of B with respect to A? Okay, that's what I'm gonna ask you, and I'm gonna consider 2 individuals, A and B. A is jogging along the positive direction of the x-axis at a speed of 2 meters per second, and B is walking along the same direction, with a speed of 1 meter per second. So what is the velocity of B with respect to A? Remember, this is a one-dimensional example. I'm going to put that here. One-dimensional example of relative velocity. So you can start having an idea about this concept, okay? So going back here, my drawing, right? Okay, the way you do it is just subtract 2 from 1, right? And then if the ground see this guy moving at 2 meters per second, this other individual here, individual B, is going to see this guy here moving at 1 meter per second, moving away at 1 meter per second from his own referential, okay? It is as though as this individual had his own referential attached here. And I'm even going to say that the referential of this individual is B, referential B. Okay? There is a very nice equation that you can memorize easily. Okay? And there is a very simple derivation for this equation too. This one, you're just analyzing them, right? You can see that there is a difference in velocity. You can see that B is moving away from him. Consequently, his relative velocity is going to be positive. And there will be a difference here, 2 minus 1, that's going to be 1 meter per second. But there is a more formal way of deriving that in terms of actual equations. And the equation is rather easy to memorize. It's not difficult. It's rather easy to memorize. And the way you do it is like that. It's the following. Okay? Consider now, I'm going to get rid of this guy here. Consider 2 referentials A and B, okay? Consider 2 referentials A. This one here is going to be B. This other one here is going to be A. The more strict treatment, right? The more formal treatment is done this way. Referential B is moving away from referential A with a relative velocity that we call velocity of B with respect to A. Okay? I'm not going to put numbers there. I'm just going to write down like that. Velocity of B with respect to A. And so let's say there is another object here. I'm going to call object point P. Has a specific velocity vector. Can be either with respect to A or with respect to B. Okay, remember, I'm doing a more generic treatment. And now this guy here, can be a velocity in any direction. Any direction that I want. And let's say that's velocity of P with respect to A point P. Find the velocity of point P with respect to B. Given the following problem, right? And I'm going to copy this guy here. In this case, let me finish this example, right? In this case, okay, velocity of A with respect to B is going to be 1 meter per second, and it's going to be a positive direction because A is moving away from B. Okay. Now consider a more generic example in which you have two referentials, A and B, A and B, and a point P. Velocity of P with respect to A is none. You are required. Let's see, velocity of P with respect to A is none. Velocity of B with respect to A is also none, comma, find velocity of P with respect to A, okay? So mathematically, it's like that. I'm gonna put, solution. Another example. Solution. I'm gonna get my vectors right in here. My vectors, no, my equations. Solution. No, I'm gonna just set up the problem. I'm not solving it yet. I need a little bit more than that. V of B with respect to A is none. So I just put this exclamation point, okay? This exclamation point means that the velocity of B with respect to A is none. Velocity of P with respect to A is also none. Just setting up the problem, repeating what I wrote down there, okay? So what we want to do, we want to find velocity of P with respect to referential B. Here's the question mark, okay? Here's the question mark. There is a very nice treatment for this type of problem. And the way we do is like that. Okay, first, okay, we get, I'm gonna do a little bit more better, a little bit different than what I did before, okay? Consider that now the x-axis of B is displaced like that. And because of that, I'm gonna call that x prime. Oh, x prime. And we do the same for the y-axis. The primes are the axis of referential B. Okay, this referential A can be the ground, referential B can be a car that's moving with respect to the ground. A point P can be another car, or can be a pedestrian, or can be an airplane, whatever. Okay. So how do we treat this type of problem in a very generic way? And by the way, it doesn't have to be along the horizontal direction. It can be also in every possible direction, okay? That's the velocity of B with respect to A, okay? Can be something like that. So how do we treat this type of problem? We use vectors, vector position, okay? That the vector position of B with respect to A. And I gotta use, see, I want the, yeah, that's the one I want. Oh. Okay, let's do that again. Equation, yeah, here you go, now I got it. That's going to be my vector position of B with respect, going on here. B with respect, okay, good. But then I still have to put the vector equals vector. Yeah, good. Got it? This is the genetic treatment, okay? Here you go. And here, I'm going to come up with another vector position. Here you go. That's going to be the vector position of P with respect to A. It's very important that you memorize this procedure, okay? And I'm going to fill with no fill, yeah. So I can see my arrow there at the end. And finally, we are going to have this other vector, the vector position of P with respect to B. See that? It's always taking with respect to the origin of the axis. See, I'm taking from the origin of A, from the origin of B, right? Origin, and I'm even going to write down here too. This is going to be origin 0. No, even better. O, let's call it O. O. And the other one is going to be origin O prime, just to keep it with the notation. Okay? And I'm going to come up with a better axis here. I don't like this. Okay, I gotta go elsewhere. Size and position. No, I think it's format shape. Yeah, it's format shape. Let's use this one instead. Let's see if it's better. Nah, it's terrible. Maybe I have to increase the size. Maybe I have to increase the size. Yeah, I have to increase the size. Yeah, now I can see better, right? Next, this one here. Increase the size. Nope. Yeah. Okay, that's the problem. Between arrow and arrow. Okay, that was, and this one here. Yeah, now I have it right. And this other one here. This one, let's increase the size. Okay. So now we're going to investigate here all those vector positions. Just remember that the velocity of P with respect to A is going to be delta RPA over delta T, right? Similarly, the velocity of P with respect to B is going to be delta RPB divided by delta T, right? Make sense? And here, I'm going to improve my notation, right? Don't forget it's a vector, right? I want to make sure I get the notation in the proper way. And I don't need that anymore, okay? Okay, just look at this triangle that we have here. Do you see that RPA is going to be this plus this, right? Head to tail, right? Tail and head. From this drawing alone, I can write it down, 1148, we're getting there. Okay. From the drawing below, we have the following equation. And I'm going to get this one here. I'm going to copy this and put that in my snipping tool. This one right in here, right? We have the following vectorial equation. Vectorial equation. R PA, right? Vector position of point P with respect to referential A is going to be equal to vector position of referential B with respect to referential A plus vector position of point P with respect to referential B. Do you see that? This guy here is this plus this. But wait a minute. There is a better format for this vector equation. If we commute those two vectors, put this guy right in here and this other one right in here, now we have a more now we have an equation that's easier to memorize. Okay? Now we have an equation that's and how is it that gonna be easy? Okay, just notice this point P here. I'm going to put it with a color red. And I'm even going to boldface it. And I'm going to color this one with a color green. Okay. And again, I'm also going to boldface it so it's easier to see. Analyzing this right side here of the equation, notice that I have my point P that's supposed to be in red. As the first term here. And the point A and the referential A as the last subscript, right? First subscript on the left side, first subscript on the right side. Last subscript on the left side, last subscript on the right side. Do you see that? And on the top of that, whatever subscript is left is a repetition what you have in the other term. Can you remember that? This notation that you see here has some mathematical properties, right? So now that we got that, and remember, I want to find point P, velocity of point P with respect to B, right? How do we do that? Let me here write this equation. Now I'm going to get rid of this middle term, right? If you want to get velocity right in here, all we have to do is make delta R over delta T, right? Here you go. Delta R over delta delta T. I'll put it the other delta R over delta T and one more, delta R over delta T. Okay? But wait a minute. Delta RPA over delta T is in reality VPA, right? Similarly, delta RPB over delta T is going to be what? VPB. And this other one, VBA. And the notation and the notation still is carried over, right? P here, A here, A here, BB repeated, okay? And we want to find this guy right here. So what we do? We just solve for VPB, right? VPB minus VBA equal to VPB. VPA minus VBA is equal to VPB. Okay? So we managed to find a more generic equation for relative motion. Okay? But if you do not remember this equation, just recall, remember the fact that the first subscript appears first on both sides, and the last subscript appears last on both sides, and whatever is left of subscript appears only in the middle, right? And the same thing applies here for this one. We have A here, let's see, we have P here, we have P here. We have B here, but wait a minute. We do not have B here at the end. We do not have B here at the end because we have a negative sign. But if you write this vector instead of vector BA, you write them as vector AB, right? What happens here? We can change the sign because VAB going from B to A is minus VBA going from A to B, okay? Just look at this vector right here. Position of B with respect to A, and then we also have the reverse, the position of A with respect to B. One is minus the other, and it applies right in here too. And when we do that, look what we get. Let's see, P is here, right? P is here, P is here. B is here, last one on the left side, last one on the right side. And whatever is left appears in between the other two. Okay? So this notation has this that interesting mathematical property. And now let's use this equation here to solve again that problem, that simple one-dimensional problem, right? That I already gave you the result. Repeat the simple 1D problem using the above equation, right? So it's what's that? Should be, going back here, individuals A and B. Let's take a look here at the drawing, right? If you take a look at the drawing, it's easier. Right here, okay? You want to put aside. Now I want, let's say I want to find what? I want to find velocity of A, find velocity of A with respect to B, right? So here you go. I'm gonna, whatever is P is gonna become A. Okay. So here you go. P is A. A is going to become the ground, right? Different notation. A is going to become the ground, and whatever is B remains B, right? Let's see if it's right. We want to find this guy right here, velocity of A with respect to B. A, the first on both sides. B is the last on both sides. The ground is in the middle, right? We have the velocity of A with respect to the ground, which is 2 meters per second in the X direction. Positive. I'm going to emphasize that this is positive. We do not have the velocity of the ground with respect to B, but we can find just by applying that relationship that you saw right here. If you have to switch the superscript, you have to add a negative here. And instead of G plus GB is going to become minus BG. Okay? And now we do have the velocity of B with respect to the ground. The velocity of B with respect to the ground is going to be what? It's going to be 1 meter per second in the positive X direction, right? You do the math, you get that A is moving away from B at this velocity, 1 meter per second. 1201. Okay, we are done here. I'm gonna go into more details next time here, and we're gonna do, this is a one-dimensional example, okay? But we can have a two-dimensional example that's a little bit more complicated and more interesting too, okay? So we can stop now, and if you have any questions, you can stay around because I have office hours now. Otherwise, see you on Wednesday, okay, for the exam.
Thank you, Professor.
Welcome.
Professor, I have a question.
Yeah.
You just said the exam was on